In this video, I want to do some quantitative comparisons of these numbers of pounds force that they talk about in this video of the football player and the cheerleader. So first of all, I'm going to make some assumptions. I'm going to assume that the mass of the football player is 100 kilograms and that the mass of the cheerleader is 60 kilograms. Other than that, I'm just going to use this number, the 2,000 pounds and 1,800 pounds, to do our comparisons. So first we need to talk about what does that mean, a pound of force. We're not used to that in our physics class. 1 pound of force. What they're talking about here is if you were to put a pound of butter in your hand, the force that your hand has to exert to hold up that pound of butter is 1 pound of force. So basically, if you calculate the force of gravity on the pound of butter, it's a pound mass. So we usually in physics use pounds to talk about masses, not forces. But what they mean here is if you take a 1 pound mass and you convert that to kilograms and then multiply by G, you would get the force of gravity on a pound of butter, and that would be 4.45 newtons. Now remember, it's not the force of gravity that your hand feels, it's the normal force of having to hold up that pound of butter that your hand feels. And you've also learned that when an object is in equilibrium and it is stationary, that the up forces balance the down forces. So this would be equal to the force of gravity on the pound of butter. And so we have a conversion factor where 1 pound of force is equivalent to 4.45 newtons. So since I can only really think in newtons, being a physicist, I'm going to convert those two values that they quote in the video to newtons. So the football player, it said, felt a force of 1,800 pounds. So that'd be like having 1,800 pounds of butter laid on top of you. But I'm going to convert that to 4.45 newtons per pound of force to get a force on the football player of 80-10, and then the cheerleader, by falling that distance onto her back, feels a force of 2,000 newtons, and we convert that, and we get 8,900 newtons. Okay, so those are the values of the forces I'm going to use. So this is F. Now, you might not have a feel for newtons. For example, if you have a blunt blow to your skull at your temple, a force of 6,000 newtons will fracture your skull. However, if the force you did an assignment on compressional stresses and you calculated that the force to break your tibia was much, much bigger, 51,000 newtons. That's a huge force, much bigger than these forces. So it's important to quantify these two forces a little bit more to see what kind of damage they do to your body. So one common factor that people calculate is the multiples of your weight. So let's just look, how many multiples of the weight of the person are these forces? So multiples of your weight. And so it would be, remember, you feel 1 times your weight just standing there. So how many multiples for these? So for the football player, the weight of the football player is the force of gravity. So that's 100 kilograms times 9.8. And so he has a weight of 980 newtons. And for the cheerleader, her weight is 60 times 9.8. And so that would be 588 newtons. Okay, so multiples of the weight for the football player, it would be the 80-10 newtons divided by 980 newtons, and that would be equivalent to 8 times the weight. So the impact of his collision with the dummy is about 8 times. And for the cheerleader, the 100 over her weight, it's a much bigger number. It's 15 times. And so right off the bat there, you can see that it's almost double the multiple of the weight for the cheerleader. So that's one reason it's more catastrophic. Okay, another thing to look at is stress or pressure. So how is this force distributed over an area? So this tends to be the more important quantity when you're looking at damage to your body. So for example, the force that a hypodermic needle needs to pierce your skin is not very big. It's an itty bitty bitty force. But because it's distributed over a very small area, the end of the needle, it has a huge mechanical stress that's able to pierce your skin. So definition of mechanical stress is, we'll say mech stress is the distribution of the force over an area. Okay, also called pressure. But in the case of your body, we usually talk about external forces creating stress, it's usually internal forces that create pressure. So the units for this, remember, are pascals. Those are the SI units, and the definition of a pascal is a Newton per square meter. Okay, so let's look at the stresses exerted by these forces. So we'll look at, let's see, we'll take the area, and then we'll do the mechanical stress. And we'll compare. So let's say for the football player, we take it on the helmet. He takes it. If he were to take that force just on the area of his helmet, which I'll estimate to be 10 centimeters squared, the stress would be the force, the 8,010 newtons, over the 10 centimeters squared. Now remember, you guys, you know how to calculate the conversion between centimeters squared and meters squared. You multiply by 10 to the minus 4, is equivalent to 10 times 10 to the minus 4 meters squared. And so when you divide, you actually get 8.0, we'll just round it to 8.0, times 10 to the 6 pascals. And a common unit for stress is megapascals. Okay, so the mechanical stress, if you took the entire force onto just the area of his helmet, would be 8 megapascals. But let's say we increase that to his shoulders. If he were to crash into something using his shoulders, and the area there may be about 10 times that, say 100 square centimeters, then the stress would be 10 times smaller. When you increase the area, you decrease the stress. And so this would be 0.8 megapascals. If you took it to the full body, the football player, so let's just estimate that to be 1 square meter, then the stress would be 0.008 megapascals. Now, once again, here are a bunch of numbers you probably don't have a feel for, but the compressional stress, maximum compressional stress that a vertebra in the body can withstand before crushing, breaking. So the compressional strength of a vertebra is 2 megapascals. So if this football player were to take that entire force onto his helmet, he would be 4 times the compressional stress that's required to break a vertebra. So you can see why they talk about in the other video, I can't remember which video it was, it talked about the head down collision, how bad that was. So if he takes the force of the collision with his head down, so it hits the top of his helmet, you can see that on these little vertebrae here, the force, the compressional force is huge. So the compressional stress is 8 megapascals, and it's no wonder it crushes those vertebrae. Now, if he takes it to the shoulder, 10 times less, now this is not talking about compression anymore. This would just be twisting your body around. So what kind of damage that does to your body, I'm not sure. That's why you're taking the other course. And then to your full body, it's a much smaller overall pressure. And remember, it said in the video that the damage to spinal cords often, it's not from crushing things, it's from a bone chip hitting the spinal cord. So, sounds awful. Okay, let's look at the cheerleader. So what kind of stresses is her body undergoing by having a force of 8,900 newtons? So she lands on her back. So I sort of estimated that area of her back to be 0.5 meter by 0.5 meter. So that would be 0.25 square meters. So this would be for her back. And if you calculate the stress, that's 8,900 newtons over 0.5 a square meter, or 1/4 of a square meter, and you get 3.56 times 10 to the 4 pascals, which is equal to 0.036 megapascals. Not a lot of stress because it's distributed. Now, that's not putting her spine in compression or anything. That's just squishing her whole body. If you look at, if she were to land on her feet, on both feet, and so I just estimated the area of her feet, like if you sort of just take, she's got a foot here and another foot here. I estimated that area to be 25 centimeters by 10 centimeters, or 0.025. So a factor of 10, area smaller, that increases the stress by a factor of 10. Still not very big. Okay, now there's definitely something wrong with that, because it only takes you to step off a 1 meter high table and land straight-legged on your heel. There's enough compressional stress to break your tibia. Okay, so this is a little bit fishy, those numbers, but that's only one other comparison. Okay, let's do another comparison. Let's calculate accelerations. That is also a very important factor in how much damage your body undergoes. Now these are the 2 units that we're going to do this week and next week, and that is definition of acceleration, which is change in velocity over change in time. And that is the assignment that you have due this Friday. So you will have looked at this and done some calculations. Okay, so that's delta V over delta T. So it's how rapidly your velocity changes. And that's an important quantity when it comes to damage to your body. So another factor, another thing we need to know is Newton's second law. And you do know that. You have been exposed to that when we were doing torques. We will do a lot more on this, not this week, but next. So Newton's second law also tells us that F net is equal to the mass times the acceleration. So I want to see what are the accelerations of the football player and the gymnast or the cheerleader given the forces that they give us. Okay, so let's look at the football player. Now we'll assume that he leaves the ground and then crashes into that dummy. So I'm only going to count the force from the collision on his body as the net force. I'm not going to worry about the friction on his feet as he's running along. So we'll take the net force to be that force of collision, the 80-10 newtons. And so that's equal to m times a. So the acceleration as that football player feels that force would be 80-10 divided by mass of the football player. By that by 100, and you get 80.1 meters per second squared. That is a significant acceleration. And to quantify that, what we often do is we calculate the multiples of g. So we say, like, how many g's is that? So we divide by 9.8, and we get, so the number of g's is 80.1 divided by 9.8. And that's about 8 Gs. Not quite sure where I put that. Anyways, that's about 8 Gs. Now that's a huge acceleration. If you take an astronaut and you accelerate them at 4G, they're going to black out really rapidly. So you can't sustain this acceleration for any length of time. So it must be a really quick acceleration. When they take off in the space shuttle, or if you've ever been on any of those rides at Disneyland, the acceleration is about 3.3 Gs. And that's enough to make you absolutely ill. Okay, let's look at the cheerleader. It's a little more complicated with the cheerleader when you're hitting the ground, because the force they're talking about is in fact the normal force. Remember, that's the force that you feel. And so this is the 8,900 newtons. But there is also the force of gravity. Now, these are definitely not equal to each other when you impact the ground. The normal force is way bigger because it has to stop you. It's a huge upward force. It has to stop your body from continuing on down. If the floor weren't there, then you wouldn't feel that force at all. And so the net force in this case is the 8,900 minus the 588, and which is 8312. And so now to get the cheerleader's acceleration, you take that number and you divide by the mass of the cheerleader. And so this gives you a huge acceleration, 139 meters per second squared. And so the number of G's is 139 over 9.8. So this is a unitless number, it's just a factor, 14 G's. So that's a pretty good indication of how much more catastrophic that gymnast falling on her back is. Regardless of how she lands or what's going on, that's the acceleration to stop her. Oof. Okay. Now, based on those stresses, there's something fishy going on because they do not indicate how awful the crash is for that cheerleader. So what we have to look at now is the time of the collision. This is vitally important. And this is the whole idea behind airbags. If you have to bring an object to rest, so if you're barreling along at 80 kilometers per hour and you stop, your change in velocity is the same, 80 kilometers per hour minus 0, that's it. Now, depending on how you stop though and how long it takes to stop, the force required is drastically different. And so with the airbag, it slows you down in a longer period of time, much less force. So let's look at the force versus time for these two collisions. So this will be force and this will be time. Okay, on the left we'll do the football player. And on the right we'll do the cheerleader. Now, I'm assuming that when they give you these forces, we'll assume that's an average force that is exerted over the whole time of contact, either between the football player and that dummy person or the cheerleader on the floor. And so the average forces aren't that different. This was the 80-10 newtons. And then a little bit more here. Now with foresight here, I know this one goes like this. Now, how do I know that? Okay, so this is average force, this line here. This is average force. And the reason I know that this one, the cheerleader stops before, this is the time of contact, is because the area of these two rectangles represents the change in momentum. Now, we're not going to have time to get to change in momentum in this course, but the rectangular area on the graph, it's an abstract quantity, but it's a mathematical representation of change in momentum, mass times change in velocity. Now, the football player, it said he was running at 21 miles an hour. That's about 9.5 meters per second. And then he stops. And so I'm just going to use 10 meters per second. It's easier to calculate. So this would be a like super fast runner. This would be 1,000 kilogram meters per second. So the area of that rectangle would be 1,000 units here of momentum, 1,000 kilogram meters per second. The gymnast, on the other hand, so that's the football player. I keep calling it a gymnast, cheerleader. The cheerleader, this area would be her mass, 60. Now, when you fall, it said she fell from 18 feet. I'm not sure if it was actually 18 feet in the video, but 18 feet is about 5.5 meters or something. You're only going about 5 meters per second just before you hit the ground. And that we're going to do this calculation. It's how fast are you going if you fall from a certain height, neglecting air resistance. This comes to only 300. So that's why I know that the area up here is smaller. And if it has a greater height, obviously it's going to have a smaller width. Okay, so the time of the collision for the cheerleader is obviously much smaller. And you can see that. The football player kind of hits the dummy and goes, crashes into the ground. The cheerleader, boom, hits that hard floor and stops much more rapidly. Okay, now, when you have forces, that is not how the force goes, this average force. The force has to grow before you're in contact. The force is 0. Once you've stopped, the force stopping you has stopped. And so what the force actually looks like in a collision is it kind of grows, and then it kind of gets higher, and then it kind of comes down like this. Now, the area under this curve that I just drew, has to equal the area of the rectangle. That's the definition of average force. I didn't draw that very well. I should probably go up a little bit more. But the important thing is this is the peak force. That's the maximum force. Not that much bigger than the 80-10. And so all the damage that's done to the body using this average force to do the calculations is okay. It's not that bad. Here, however, when it's a very quick and impulsive force, what tends to happen, because the areas have to be the same. This one goes like this, it goes way up here like this and down. In order to get the area of that curvy one equal to the area of the rectangle, it has to go way higher. This is the peak force, and it's going to be way bigger than that 8,900 newtons. So that's the thing doing all the damage. It's a much bigger force. And so all the calculations that we did for stress on your body, you would be better off to use this peak force. Okay, so there's some comparisons. You could actually calculate this time of contact if the area is 1,000 and the height of this rectangle is 80-10. The time of the collision. Now this is another way to compare how these numbers are doing. Would equal the area divided by the force. And so for the football player, that would be 1,000 kilogram meters per second divided by the 8,010 newtons, which is a kilogram meter per second squared. This unit's going to come out in seconds. That's 0.12 seconds. And that's a fairly long time, actually, for a collision. That wasn't a very violent collision that he kind of sailed along with that dummy on his chest. So this is for the football. But the time of collision with the floor was the 300 kilogram meters per second over the height of that average forced rectangle. This is 0.03, much faster. Okay, that's like 30 milliseconds. So that's much, much faster. And that makes a huge difference to the peak force that you feel. Okay, so there's some comparisons of those two numbers in those videos. Have fun learning all about head injuries and spinal cord injuries in your other course.